we are not done with Drude model yet. The model has been around for more than 100 years, and it has its fair share of success. So, let us just try to understand a few more phenomena using Drude model, which actually helped us in understanding several experiments in the past. And so, let me just introduce you to a very important experimental experiment which is called the Hall effect. Now, Hall effect is is a way one measures the charge of the carrier in a particular medium, in a particular solid, and so it has been around for a long time, and it also tells us many more things, which is we will come back to it at a much later stage. So, again what we do is that we start from the equation of motion that we wrote down, and the geometry now is a bit different. So, what does Hall effect do? The original idea of Hall was that if a current flows in a conductor, and if we put a perpendicular field across that conductor, then of course some of the electrons will get deviated because of the Lorentz force coming from the magnetic field sorry, and this will deplete the number of electrons arriving at the other end. So, that means effectively the resistance has increased, and so he was looking for the increment in resistance due to magnetic field. So, the geometry is simple. Let me just draw the geometry. Again a slab of conductor, and so in this situation, let me just draw the axis also. So, Z, this is x, y and z, and the electric field is along this direction, along x direction. There is a magnetic field perpendicular to this, which is along the z direction, equal to 0 0 b, its magnitude is b. And then because of this, let me just show you what will happen. There is this Lorentz force V cross B by C into minus E. This Lorentz force component coming from the magnetic field will just turn the electrons, and what will happen is that there will be a concentration of positive charges on that side and a negative charge on this side. So, that means an electric field gets generated in this direction, in the transverse direction, y direction here, and that field actually opposes the further movement of electrons. So, this field basically cancels the force that comes from the Lorentz force. So, and that is where the equilibrium is attained. So, let us just calculate it, and first let me show you the directions. So, this is my B along z direction, and this is the direction of, see, this is Vx, and this is minus E V cross B by C. Remember, the currents are flowing in this direction, that means the electrons are flowing in that direction. That is why I have drawn the V sub x in this direction. So, there are quantities that one needs to define. One quantity that is there are two quantities that one defines here. One is this quantity, which is standard Ex by Jx, is called magnetoresistance, simply because there is a magnetic field. Had there been no magnetic field, this is just the resistivity that we would calculate, but because there is a magnetic field, this is called a magnetoresistance. And then there is another quantity that is very important, which is R sub h, called Hall constant, whose definition is E y by J x into B. Why does one choose this kind of a constant? See, for example, this E y, as we said, is the field that is generated due to the movement of electrons, their accumulation of electrons on this surface and that surface. So that means that this E y should be proportional to the current. It has to be proportional to the current, because the electrons move, the force is because of the velocity of the electrons, the speed that the electrons are moving. In addition, it is also caused by the magnetic field. So, it should be proportional to B also. So, E y, if this is a constant, which it is, then E y is proportional to J x and B. So, that is why this constant was chosen, and it is called the Hall constant. Our aim is to determine this constant. Okay. So, let us just go ahead and do the calculation. See, the Lorentz force is minus E by minus E electric field plus minus E V cross B by C in Gaussian units. Now, if you do that, this part gives me minus E, that is the electric field, minus E by C. So, let me just show you what it is. Simple cross product E by C. Remember, B is 0 0 B. So, I will have no z component of velocity involved here. I will have minus V y into B plus V x. So, these are the two components, V y into V x into B. So, the x component is minus V y into B, and the y component is V x into B. Okay. Okay. Now, under this force, let us calculate the from the equation that we already had, and try to find out what happens to the numbers that we wrote down, the Hall coefficient and the magnetoresistance. So, dp dt equal to minus E plus V cross B by C, okay, and this term that we derived, the relaxation term, the drag term, or whatever it is called, I mean usually called drag term, or just the term, the relaxation term. Now, in the steady state, of course, as we did the other day, we will put this to 0. So, therefore, I have two equations. One is for the x component, which is minus E x. Remember, the field I started with was along x direction, but then another field has now generated, which is in the y direction because of this term. So, I have to keep both the fields, minus E b by m c into P y minus P x by tau. Okay. Now, basically what I have done is V I have written as P by m, which will do for the y component also, minus E y plus E b by C into m into p x minus p y by tau. So, these are the two equations that I have to simultaneously solve. Okay. So, let us define. This definition is a very standard definition, this you will encounter later also. So, this E b by m c is usually written as omega sub c. We will come back to it when we do electrons in a transverse magnetic field again. And also what we do is that multiply the equation, both the equations, by minus n square tau n square minus n e tau by m. See, you can see the logic for doing this, because if we use this multiplication, these terms will become n square tau by m, and there is a E b by m c. So, I will have a omega c times tau. So, that gives me the equation that sigma 0 E x equal to j y into omega c tau plus j x see the we have already I am using the fact that j equal to minus n e v. So, the other one is sigma 0 E y equal to minus omega c tau j x plus j y. So, these are the two equations that I have. They need to be solved. Now, the what I want is this Hall resistance, and for that I have to put the current in the y direction to be 0, because that is when the equilibrium has reached in the steady state. So, no more current is flowing in the y direction. So, that gives me j y equal to 0, and if I do that, then E y from this equation E y is equal to, so okay, let me just write the full thing, E y by j x into b. You can calculate this equal to R h will turn out to be 1 by n e c with a minus sign. This minus sign is very important because now this is the definition, this is how I defined R h. So, R h turns out to be minus n e c. So, this minus sign tells me that these the carriers here are electrons. If there is if this appears with a positive sign, then what I can assume then is that the carriers in the system are of a opposite sign to the electrons. That is what happens for example, when you have holes carrying the current, which we happens, which we know happens in metals or semiconductors sometimes. So, this relation actually is a celebrated relation. This is the Hall constant, which tells us the sign of the carriers. So, I will actually ask you to remember this, because this is such a simple relation. It only depends on the density and then two fundamental constant, electric charge and C with a minus sign. So, that is what one is really after in experiments, and once you do experiments, what you will find is that this relation is more or less valid in many metals. However, there are systems where the sign is different, which I say I actually preempted that, and I said that there are different kinds of carriers, that is indicative of the fact that there are different kinds of carriers in a system which are positively charged, which actually brought in the idea of holes. And of course, the other problem with this is that this relation is not always valid. Such a simple relation does not work out always. This n is of course temperature dependent a bit. In a metal it is not so strongly dependent, but this simple relation fails in many materials, but it is still a celebrated relation because for many systems it works out, and it gives the it's one way of one of the very few ways in which you can determine the sign of the charge of the carriers. Okay. So, now just let me wrap it up this discussion by showing you one more simple application of these equations that we got, and then I will be done with it, which is what I have been mentioning from the beginning, that this dp dt, the dynamics, has so far not played much role in these deductions that I have done. We have always set the steady state condition and set dp dt equal to 0, but there are situations where it is not, and one such situation obviously is where there is a electric field. So, when there is a electric field that is time varying, then that case this will not be 0. It will follow the time dependence of the electric field, and we can work out the equations of motion, equations for conductivity in such a situation. I will show you that the conductivity becomes a complex number in this sense, in this case, and it becomes frequency dependent. So, let me just show you in it is a very short calculation and anybody can do it easily. So, this is what I will work out now. So, suppose there is an electric field which is varying in time as with say a single frequency, and this I denote by real part of some e of omega e to the power minus I omega t. Okay. Then my I will use this equation dp dt equal to minus p by t plus the force coming from here, and I remember that since E is varying with a single frequency, my momentum, the electron momentum, will also vary with the same frequency. So, I can write my momentum of the electron as the real part of p of omega e to the power minus I omega t. Now, of course, what I can do is that I simply substitute these two complex representations of the field and the momentum in this equation, and I get in this equation, for example, the one that I have been writing, pi p by tau minus E E. Okay. So, this equation now becomes minus I omega p of omega, simple time derivative will give you that is equal to minus p omega by tau minus E E omega, because e to the power minus I omega t gets cancelled from both sides. Sorry. So, that is the equation. Now, this equation is very easily solved. I mean, you can just write down the current from this equation. So, current is again I can assume the current to be following this frequency, this so this current is again real part of j of omega e to the power minus I omega t, and j equal to NeV for electrons, right, equal to minus N E P by m. Okay. So, if you combine these two, then your j omega is j omega turns out to be, you just put it back here in this equation, yeah, this equation, So, then j omega is equal to minus n e p omega by m equal to n square by m into e of omega by 1 by tau minus I omega. Now, this is a very important relation. This just comes by replacing this p of omega. From here you can replace p by j times m by n e, the minus sign, and that will give you this relation. So, that it is from the relation j omega equal to sigma omega. Now, everything is frequency dependent, remember, e omega we can easily calculate, find out basically that sigma of omega equal to sigma 0 divided by 1 minus I omega tau, where sigma 0 is n square tau by m, the good old DC conductivity. So, that is what happens when you have a time varying electric field applied to the system. The conductivity is now a complex number, and this complex behavior is dictated by sigma naught divided by 1 minus I omega tau. In most cases I omega tau is a very large number, and then of course, in that case you will recover, you will have sigma 0 by I sigma 0 by omega tau. If omega tau is a small number, then of course, then that means that your frequencies are very low, and you go back to the DC limit, which is sigma 0. But typically generally these frequencies are fairly high, particularly for electromagnetic radiations. These are in the terahertz region, 10 to the power 15 hertz or so. So, there you have to actually keep it. From this relation you can go one step up, and you can use Maxwell's equation. You can use Maxwell's equation and combine with this result that j omega equal to sigma omega E of omega, then you will find a very useful identity, which is the dielectric constant, which is our good old dielectric constant, which is now 1 minus omega p square by omega square, where omega p square is 4 pi n e square by m. Now, if the dielectric constant has to remain positive, then then this omega has to be greater than omega p. So, that means it this quantity has to be less than 1, whereas if omega is less than omega p, then there is a trouble, because then it becomes a negative number. This goes into the frequency and in the e to the power I omega t, and then it becomes a complex number, and that means there is a decaying part, which means that your frequency, if it is not more than omega p, which is called the plasma frequency, then electromagnetic radiation will not penetrate into the system, it will decay down, whereas if it is greater than this, then it will go through. So, oscillatory radiation will propagate, and the metal will become transparent if your omega is greater than omega p. So, this relation is actually very useful, and the value of plasma frequency is typically around, as I said, in the 10 to the power 15 hertz range for typical metals. So, a conclusion from this simple classical model with a relaxation time approximation tells us that a metal can be even transparent to to a electromagnetic radiation, oscillating electromagnetic radiation, or the radiation can decay. So, a lot of useful physics can be obtained from a simple model like this, and that is why Drude model has been studied for so long. I mean, it has not run its course. Many simple minded pictures can be obtained from this extremely simple and classical model of Drude. So, what we have done today is basically we are concluding our discussions on Drude model. We will come back to it, not just not a discussion of Drude model, but some of the successes and failures at some point in the future. But basically it shows that a model of such simplicity, treating electrons as a classical gas with a relaxation time approximation, gives us so many useful and interesting results, and the discussions are all classical. There is no quantum mechanics involved in this, and still we get very useful results which tells us the story of a metal both in static condition as well as in under oscillating electromagnetic field. Now, apart from that, there are situations, of course I must admit, where Drude model fails quite miserably. For example, specific heat is a great example. You just saw that specific heat in Drude model is still assumed a classical 3/2 Nk, which is not what happens in a metal. It goes linearly with temperature. The success of Wiedemann-Franz law from Drude model is also a bit qualified in the sense that it works out at low temperatures and at high temperatures, but there is a large range of temperature where this constancy, that Lorentz number being a constant, does not really work out. But nevertheless, it is still a very useful model, and it has not run its course for nearly 100 years now. So, for many simple metals where electron correlation is not very strong or other anomalous effects exist, if you leave aside those, for many metals it works, and it gives you very nice results. So, next lecture onwards I will leave this Drude model and start using quantum mechanics, which is what finally dictates the world of electrons, and one has to calculate things starting from quantum mechanics, and quantum mechanics of many electrons. So, the interactions might become important. We will discuss all of that at a later stage, but at the moment we will start with simple non-interacting electrons, but with quantum mechanics, and see what comes out of it. It is a completely new world. Thank you so much.